Welcome back. This is now the 16th lecture of the condensed matter course. When last we left off, we were talking about band structure of solids, and in particular, we were thinking about the nearly free electron model as a way of understanding the band structure. A summary of the most important things we learned is really given by this one picture here. So you have the free electron parabola, and due to the periodic potential, you can scatter from Brillouin zone boundary to Brillouin zone boundary, and you open up a gap at the Brillouin zone boundary. You can also view it in reduced zone scheme if you prefer. Now, one thing that's really important in this picture is to realize that states that are in the extended zone scheme, states that are inside the first Brillouin zone are pushed down, whereas states that are outside the first Brillouin zone are pushed up. So maybe I'll write that generally. States inside BZ boundary pushed down, and outside are pushed up. Outside pushed up. And the closer you are to the Brillouin zone boundary, the more your energy is changed from the free electron model. So let's see if we can take this principle and understand what happens to various Fermi surfaces when we go to higher dimensions. So let's consider two dimensions, square lattice. So we have a square Brillouin zone. So square Brillouin zone, I'll draw a square Brillouin zone. Here it is, square. K equals 0 is in the middle. This point over here is pi over A, at the corner. And let's consider first the case of 1 electron per unit cell. So that means we should have a 1/2 filled Brillouin zone, half filled lowest band or a half filled Brillouin zone. So what happens? Well, in the absence of scattering potential, you just have a nice Fermi circle or a Fermi sphere. Well, in 2 dimensions, it's a disk, I guess. And this is actually a fairly good representation of many monovalent materials that have 1 electron per unit cell. For example, sodium. So here's the 2-dimensional analog. You just have a disk filling exactly half of the area of the Brillouin zone. So this circle is supposed to fill exactly half of the area of that square. Sodium is a BCC material, so its Brillouin zone is this funny wired shape. It's a rhombohedral dodecahedron or some strange shape like that. But inside it, filling exactly half of the volume, is a spherical Fermi surface, which tells us that sodium is nearly a free electron system because its Fermi surface is almost perfectly spherical. Now, what happens when we add a stronger periodic potential, where we let the periodic potential start moving around the energy of certain states in the Brillouin zone? Well, what happens is the states near the Brillouin zone boundary, but inside the Brillouin zone boundary, get pushed down in energy. And the states that are closest to the Brillouin zone boundary get pushed down the most. So if you consider a state around here, this is pretty close to the Brillouin zone boundary, so its energy is getting pushed down more than a state here whose energy is getting pushed down less. As a result, the Fermi surface wants to deform in such a way that more states around here are going to fill. So it's going to sort of deform like this, such that more states near the Brillouin zone boundary are filling because they're getting pushed down more in energy than the states which are farther from the Brillouin zone boundary here. So you'll get a Fermi surface that kind of looks a little bit more like this, a little bit deformed due to the shifting around of the energies of the states in the Brillouin zone. And in fact, that's what we get for lithium, which is again a monovalent material. So its Fermi surface should fill half of the first Brillouin zone. Again, the same shape of the Brillouin zone. It's a BCC material. And you can see, oh, here's the 2D analog drawn a little bit better than I drew on the board. And you can see that what's happened is where the Fermi surface, which is basically spherical, comes close to the Brillouin zone, it's pulled out towards the Brillouin zone boundary because those states which were close to the Brillouin zone boundary have been pushed down more in energy than the states which are further from the Brillouin zone boundary. Okay? Does that make sense? All right. Now, in fact, if the periodic potential becomes extremely strong, what can happen is the states right at the Brillouin zone boundary can be pushed down so much that they go below the Fermi surface, in which case the Fermi surface deforms until it actually touches the Brillouin zone boundary, and you get something that looks more like this. and the states inside that shape are filled, and the states outside that shape are empty. And that's exactly what happens with the material copper. Also a monovalent material. It's actually an FCC material, so the shape of its boron zone is different. It's this truncated octahedral shape that we've seen before. And you can see that the, oh, here's a picture in 2D, which is drawn better than I've been able to draw it on the board. You can see that the Fermi surface is basically spherical, roughly spherical, and fills exactly half of the boron zone because it's monovalent, and 1 electron per unit cell should fill half of the first boron zone. Where the sphere comes close to the boron zone boundary, the states near the boron zone boundary get pushed down in energy, and those states preferentially fill compared to the other states which are farther from the boron zone boundary, which are over here, which are pushed down less, and those states become empty. So is that clear how the shape of the Fermi surface is getting deformed? All right, so that's one interesting case. Let's consider another interesting case where we have 2 electrons per unit cell. So here, 2 electrons per unit cell. Again, we have the boron zone. Here's K equals 0 in the middle. Now, in the absence of a periodic potential, again, we should just have a Fermi circle, or a Fermi disk, I guess, whose volume is exactly the same as the first boron zone. So area, in this case, equals the same as boron zone, BZ area. If there's no periodic potential, then of course the boron zone doesn't matter. There's no periodicity at all. You don't have to pay attention to the boron zone. You just get a perfect circle. However, if the periodic potential is strong, then what happens is all the states inside the first boron zone are all pushed down in energy. The states outside the first boron zone are pushed up in energy, and instead of having a Fermi circle, what you get is you fill the entire first boron zone and you empty the entire second boron zone. You get a filled band and a gap and an empty band. The gap opens up so much that all the states in the first boron zone are lower than all the states in the second boron zone. You get a filled band, a gap, and an empty band, and you get an insulator. So these are the 2 possibilities. With no periodic potential, it's a perfect circle, which you can view, if you like, as filling part of the first boron zone that's inside the square and part of the second boron zone that's outside the square. With a strong periodic potential, everything in the boron zone is pushed down in energy, so everything fills in the first boron zone, filled band, then there's a gap. Everything in the second boron zone is pushed up in energy, so there's a gap between the filled band and the empty band, and so we have an insulator. Okay, so that's the simple part of it. The more complicated part of it is what happens when the periodic potential is weak, or intermediately strong. In that case, what happens is that some of the states in the first boron zone are pushed down in energy, and some of the states they're all pushed down, but they're only pushed down a little bit, so only some additional ones fill. So the ones that are sort of lowest in energy that haven't been filled are states here. So these states will start to fill in addition to the states that were already filled, and some of these states will start to fill in addition to the states that were already filled. Some of these states up here, and so forth. And we'll start filling in the corners that we haven't filled in already. But if the potential isn't sufficiently strong, we won't fill in the entire first boron zone. We'll leave a couple of states in the corners which are empty. Here, still empty, still empty. And the reason these states in the corners are the ones that are still empty are because these are actually the highest kinetic energy states in the first boron zone. They're the farthest from K equals 0. So those should be the last ones to fill. Because they have the highest kinetic energy, they would have to be pushed down the most before they go below the Fermi surface. Similarly, in the second boron zone, all the states are pushed up in energy. The ones that remain filled are the ones with the lowest kinetic energy, these little slivers here. Everyone else empties, but these little slivers remains filled. So now I have a picture of it, which is better drawn than I can draw. So it will look something like this. Most of the first boron zone is filled. The corners are empty because those are the highest kinetic energy states in the first boron zone. Most of the second boron zone is empty, except these little slivers here, which remain filled because those are lowest kinetic energy states that are closest to K equals 0 in the second boron zone. So this is still a metal. It still has a Fermi surface, a point where the empty states meet the filled states within the boron zone, so it's still a metal. Here you can have low energy excitations. Now, the way this is typically drawn is to view each band one at a time, or each boron zone one at a time. So you just draw the first boron zone. You have this picture here. It's mostly filled with just some corners which remain empty. And the second Braun zone, well, we draw it in reduced zone scheme. We can sort of translate everything back to within a single Braun zone. So this piece here gets translated to over here by 2 pi over a. This piece here gets translated to here by 2 pi over a. This piece here is translated to down here. This piece here is translated to up there. This is the usual reduced zone scheme. You move everything over until it's all within a single square Braun zone. And it would be only these little pockets that remain filled in the second band or the second Braun zone. Okay? Now this may look a little bit unnatural, but this is in fact exactly what happens in many divalent materials with 2 electrons per unit cell. For example, calcium. Now this may look a little complicated, but let me walk you through it. This is the actual Fermi surface of calcium. In the second band, so it's an FCC material, so it has this truncated octahedral shape. Here's the second Braun zone, written in reduced zone scheme, so it looks exactly like the first Braun zone. And you can see that what's going on is there's just these little yellow regions where electrons are still filled. They're just like these little pieces here peeking into the second zone, just little caps, little regions which still haven't quite been emptied. And these pieces are actually the lowest kinetic energy points in the second Braun zone, just like these pieces here were actually the lowest kinetic energy points in the second Braun zone. They were closest to k equals 0. They're in the center of these faces. Now this picture is a little bit harder to parse, but to see what's going on here, the places which are transparent are where the Fermi surface has actually hit the Braun zone boundary, and then it's not drawn. So this great big hole here is where the Fermi surface, where the electrons fill all the way until they hit the Braun zone boundary. And the places where it's not filled all the way up to the Braun zone boundary is where it's drawn yellow. So you see these little corners here, similar to these corners here along these edges. These edges are the points which are farthest from k equals 0 in the first Braun zone. So k equals 0 is in the center. The places closest are all filled up, just like these are filled up all the way to the Braun zone boundary. The points farthest are the points along these edges, and that's where it's painted in yellow, where the Fermi surface has not yet hit the Braun zone boundary. Let me draw it a little bit bigger. There it is. So in fact, with calcium, even though it's divalent, it has 2 electrons per unit cell, it actually has two bands which are partially filled. The first band is partially filled or mostly filled, and the second band, although mostly empty, still has a couple of electrons in it, so it's actually metallic. Okay? So this is sort of the general structure of a lot of bands in many materials. So for this lecture and for a couple of the next lectures, we're going to talk an awful lot about band theory and the ramifications of band theory and the physical things that you can deduce about actual materials by thinking about band theory. And remember that what we're doing in band theory is we're giving energies to every crystal wave vector in the Braun zone, and we know that these crystal wave vectors actually correspond to modified plane waves, or what are known as Bloch wave functions in Bloch's theorem. And this is a very good way to describe the physics in many of these materials, thinking in terms of these modified plane waves. But actually, we should be warned that there are some failures of band theory. And we'll discuss some of them now, and just briefly, and then sort of in the last couple lectures of the term, we'll come back and talk about some of them again. Band theory. So just to be aware that these exist. One major failure of band theory is that sometimes, although maybe rarely, monovalent materials, valent unit cells, can be insulators. And according to band theory, that should never happen, because if you have a monovalent or a trivalent unit cell, if you ever have an odd number of electrons per unit cell, maybe I should say odd valent in general, odd valent, any odd valent unit cell can be insulators in general. In band theory, this should never happen. If you have an odd valent unit cell, you should have a partially filled band, and so it should be metal. So we have to ask ourselves, what did we leave out? Well, what we left out is interaction between electrons. Interaction, why? Because we left out electron-electron interaction. Electron-electron interactions. If these are strong, they can make the material an insulator, even though by counting electrons, you would think that it's a metal. And let's try to understand roughly why that is. So imagine you have a bunch of atoms lined up in a row like this, and assume it's monovalent. Monovalent. So it's 1 electron per unit cell. But suppose the interaction is very strong. Suppose V Coulomb is very strong. Strong. If the Coulomb interaction is extremely strong, then you might have a situation where there should be no 2 electrons on one atom. On one atom. So never should you find 2 electrons on one atom, because the Coulomb interaction would make that energy extremely high and very unfavorable. So if that's true, then what you have to have is you have to have a situation where there's 1 electron on every site. Okay? 1 electron, 1 electron, 1 electron on every single site. Then you ask, can these electrons move around? Can they hop from one site to the other? Well, imagine this guy trying to hop with some hopping matrix element T to his neighbor. Can he hop to his neighbor? He can't, because there's someone already sitting there, and the Coulomb interaction is preventing you from having 2 electrons on one site. High energy from having 2 electrons on one site because of the Coulomb interaction, so you can't hop. So what you get is effectively sometimes called a traffic jam of electrons. Jam of electrons, are more frequently known as a Mott insulator, after Neville Mott, a British Nobel laureate who described it for the first time. And roughly, in order to get a Mott insulator, you have to have V Coulomb much stronger than the hopping. And sort of understanding why this is. Remember, the reason electrons hop and form plane waves is because they can lower their kinetic energy by spreading out their wave function from one site to another. This is the usual Heisenberg uncertainty. If you can spread out your wave function, you can delta x, delta p, you can make delta p lower, and then you can make your kinetic energy lower. But so it wants to form, the electrons want to spread out because of the hopping. How much does it lower its energy? It lowers its energy about T if it hops from one site to another, if it's allowed to spread out its wave function. But if the Coulomb interaction is much, much stronger than the hopping, then the electron would gladly sacrifice the amount of kinetic energy it's gaining by forming a plane wave in order to prevent itself from ever sitting on a site where there's already another electron. In which case, it will set up one of these. It's a very classical picture of just 1 electron sitting on each site, and there's no quantum mechanics has to be considered at all. It's just 1 electron on each site, and it's an insulator because no one can move, because no one wants to sit on the neighboring site because there's already an electron there. Okay? So this effect is completely left out of band theory, and so it's kind of a failure of band theory, and at the very end of the course, we'll come back and analyze this again. A second failure of band theory, failure 2. Failure number 2 is magnetism. Magnetism, such as, or maybe I'll say ferromagnetism, which we haven't defined yet. Materials such as iron, where the number of upspin electrons is greater than the number of downspin electrons, or maybe it's not equal to the number of downspin electrons. You can have a different number of upspin and downspin electrons, a non-zero magnetization, even in the absence of external magnetic field, even when B equals 0. B external equals 0. B external. And this is something that should never happen in band theory. In band theory, you should fill up both the up electrons and the down electrons to the same Fermi energy. If they were filled up differently, you could save energy by flipping over some up electrons and turning them into down electrons and leveling out the 2 Fermi surfaces. It would save you kinetic energy to do this. The reason this happens is something we'll come back to at the end of the course. This is also due to interactions plus quantum mechanics plus quantum. And it's totally outside of of traditional band theory, where we're treating only plane wave states, and energies of up electrons and down electrons should be treated on even footing. Okay? So these are things that we should just keep in the back of our head, places where band theory is going to fail. Okay? But for most materials we're going to think about, band theory is a very good way to think about it. So we're going to go ahead, blaze on with band theory, and see how much we can understand about materials by thinking in this band theory language. So the first thing we're going to think about in band theory is optical properties of solids in band theory via band theory. So first of all, what do I mean by optical properties? What I mean by optical properties means what wavelength of light is absorbed, transmitted, or reflected. In other words, if you put your material in white light, which is where we usually put it, what wavelengths of light actually reflect off of it and go into your eye and give that material the color that you actually see. So let's remind ourselves a couple things about light. Visible light, you might recall, ranges from wavelengths of 740 nanometers, which is reddish, all the way up to about 400 nanometers, which is violet. And this is all you can see, or most people can see at any rate. And if you think about energies of photons, this is about 1.7 electron volt photon, and this is about 3.1 electron volt photon. And in between red and violet is the whole rainbow spectrum: red, orange, yellow, green, blue, indigo, violet. The usual thing. Now let's think about how it is that light is going to interact with some solid in band theory, how this type of light will interact with our material. So we draw some sort of band diagram. So here's E, here's K. I'm not going to draw the whole Brillouin zone. I'm just going to sort of sketch some, diagram. This will go off to all directions in K space, and maybe a diagram like this. So this will be a filled valence band. So imagine you have a filled valence band here. Filled valence band. We have a gap here, E gap. And then we have an empty conduction band. Maybe I should define what I mean by E gap generally. So E gap equals min conduction band energy, minus max valence band energy. So difference between this energy here and this energy here. So if this is a big gap, it's an insulator. If it's a small gap, it's a semiconductor. The chemical potential is somewhere in the middle of the gap. So now let's ask, how is it that visible light is going to interact with our insulator here? Well, some photon comes in with some energy, h bar omega. And if that photon energy is bigger than the gap, then it can excite an electron out of the filled valence band up to the empty conduction band. It absorbs the electron, and that energy is taken up by the transition between the low energy state and the high energy state. Sorry, did I say it absorbs the electron? It absorbs the photon, and the electron, it gets excited from by jumping up from the filled valence band up to the empty conduction band. So what this means is that an insulator with gap, E gap, greater than 3.1 eV is transparent. Why is that? Transparent. Well, if the gap is greater than 3.1 eV, then any photon you can see, any visible photon, does not have the energy to excite an electron to the from the valence band to the conduction band. Okay? That's the key point. If the photon doesn't have enough energy to excite the electron between the two bands, then basically the photon can't interact with the electrons at all. The photon just has no choice but to just go completely through the solid without interacting at all, because it can't make any of these transitions. So we know plenty of materials like this, where the gap is greater than 3.1 eV, and therefore they look transparent. Diamond, quartz, window glass, although it's not crystalline, alumina, gallium nitride, all these materials which are transparent, they have energy gaps greater than 3.1 eV. Now, if you have a smaller band gap, smaller gaps, smaller E gap, then light is absorbed. Only photons with h bar omega greater than E gap can be absorbed. So some colors are absorbed and some colors are not absorbed, and this gives many materials the colors that we actually see. So let me show you a couple examples. So down here is our usual rainbow with the energies of the photons written on them, 1.7 eV up to 2.6. Way out here is about 3.1 eV. If you look at this material, cinnabar, it's mercury sulfide. Its gap is about 2 eV. And this material looks red because all frequencies except for red has a low enough frequency that it cannot make any of these excitations, so that the material is transparent to red. Its frequency is lower than E gap, so it must go through, whereas other frequencies are just absorbed. So the material looks red because the light coming through that material is red. All the other light frequencies have been absorbed. If you look at this material, realgar, it has a slightly larger gap, 2.4 EV, well, all the way out here. And it looks a little bit more orange because the red, orange, the yellow, and even some of the green gets through the material. And all the higher frequencies, the blues and the violets, do not get through the material. They get absorbed. So this actually ends up looking kind of orange. Now, you might say, well, how come it doesn't look a little bit more green than orange? But it's a little bit more complicated. You have to sort of average over all these colors that get through. So the middle of the colors that get through is somewhere around orange. And plus, there can be some other effects going on. But roughly, the reason this looks orange is because the blues and the violets have been absorbed. And the colors that actually go through without making any excitations and without getting absorbed are the reds and the oranges. Similarly, sulfur has an even larger gap still, 2.6 eV. And now the color that you see is pushed even farther out. It looks more yellow because the reds, the oranges, the yellows, some of the greens, and even a little bit of the blues get through that material. And so it sort of on average looks kind of yellowish. The violets have not gotten through, okay, that they've been absorbed. So this gives many materials their colors. The story is a little bit more complicated than I've told you, because the structure, the actual details of the band structure can matter a lot as to how strongly something is absorbed or not absorbed. And the most important issue, and let me draw again here, is I'm going to draw a random band structure. So here's a filled valence band, part of a filled valence band. Now you could have a conduction band here that looks kind of like this, like that. And so you can have a situation where where you can make a transition from here to here over different Ks. This is known as an indirect transition or an indirect gap. Maybe I'll write down the definition over here. So an indirect gap or an indirect transition, indirect gap equals a gap between different Ks. And then you can have a direct transition like this. This is known as the direct gap. Direct gap. I've also drawn a direct gap over here, which is a gap between the same Ks. Direct gap equals gap between same Ks. Same Ks. And it turns out to matter a whole lot for its interaction with light, whether the gap is direct or indirect. And let's think about why this is. Well, let's recall that light, frequency of light, is c times k, and c is huge. We've run into this problem before. So if we're trying to conserve both energy and momentum by absorbing a photon, the photons, for any reasonable frequency that's not like X-ray frequency, for any light frequency, if you put in a light frequency here, k is tiny. Okay? So when a photon is absorbed, if you're conserving momentum, the electron basically has to go straight up. It can't, the photons do not carry large amounts of momentum. They only carry tiny amounts of momentum because the speed of light is so large. Is that clear? Obvious? Yes? Okay, good. Thank you. Thank you for answering. I should even give you a chocolate for answering. Okay. So what we have is that direct gap transitions have strong light absorption. Strong light absorption. Whereas indirect gap transitions, are very weak absorption. Now you might wonder, weak absorption, why it is we get any absorption at all with an indirect gap transition. Okay, there's a couple of reasons. You might think if you have to conserve energy and momentum, if you can't conserve energy and momentum, there should be no absorption at all. But in fact, there's more complicated ways where you can conserve energy and momentum. For example, you can get one photon in, goes to one electron excited plus one phonon excited. And if you do this, then the momentum change of the electron can cancel the momentum of the phonon. You have the electron going off one way and the phonon going off the other way, and you can still conserve both energy and momentum. But this is a much more complicated process and occurs much more rarely than just the straight direct gap absorption. Another way that you can get weak absorption is imperfect momentum conservation, K conservation. Now, why is it that you should conserve K only imperfectly? Remember that the reason that K, this crystal momentum, is conserved in the first place, that all conservation laws come from symmetries, and the symmetry that forces us to have K conservation is translational symmetry by a lattice vector. So that assumes that you have a perfect crystal. So in a perfect crystal, K is absolutely conserved, but if there's disorder, this is from disorder or impurities, from disorder and impurities, then K is not perfectly conserved anymore because the system isn't translationally invariant anymore. So that K will be not perfectly conserved, and you'll get some amount of absorption via the indirect gap. So the actual physical absorption as a function of energy, so h bar omega here, here's absorption. This is going to be a very cartoon. I'll write cartoon on it. That when you get to the frequency, which is the indirect frequency, if there is an indirect transition frequency, it could be the case that the lowest energy excitation is direct, in which case, this just occurs when you get up to that frequency, and at any higher frequency, you'll get this plus other things as well. But if the indirect, like that picture there, if the indirect gap frequency is lower, you'll get weak absorption at the indirect frequency, weak. But when you get up to the direct gap frequency below the indirect gap frequency, you get no absorption. Then when you get to the direct gap frequency, you get strong absorption when you get above this direct gap frequency. Okay? So this is sort of a cartoon of the absorption as a function of frequency when there's an indirect gap and a direct gap. So let's actually look at real data. The real data isn't quite so nice, but you can see a little bit what's going on. This is silicon. Silicon has an indirect gap and a direct gap with an indirect frequency which is lower than the direct gap frequency, like I've drawn up there. And the energy is increasing as you go to the left. The wavelength is getting smaller as you go to the left. And you see that the absorption actually keeps increasing as you change the frequency. But when you get to the indirect gap, there's a little bit of a glitch. Now, this looks like a small glitch, but it's a logarithmic plot. So if you plotted it linearly, it would actually be a fairly big step. But it keeps increasing. But then when you get to the direct gap frequency, there's a really big glitch. Again, this is more or less a factor of 10 from here to here. And, so you get a big step when you get to the direct gap frequency. There's lots of other processes that give you weak absorption everywhere else, more complicated processes involving phonons and involving other stuff too. So it's not quite as simple as I've drawn here, very figuratively, but at least you get the general idea of those two pieces of physics. Okay, so the physics in metals, you've studied metals a little bit before, probably in your E&M courses. They appear shiny and reflective. And the reason they appear shiny and reflective is because they have high conductivity. High conductivity. And I think you probably studied this in your electromagnetism course. By metals reflect. Did you do that? Yes? Yes? Hopefully, yeah. Okay. So really what you're asking about is the conductivity as a function of omega, and from that you can get optical properties. Optical properties. But again, we have, let me draw, you have some bronze zone here. Here's a metal. A metal is a half-filled band, so we might have a metal like this. Now, the optical properties at some high frequency will depend a lot on where the second band is. If you can make transitions up to a second band, that will change sigma over omega. Even though at low frequency this thing may be a very good metal and the electrons will move very freely, if you're thinking about the conductivity at high frequency, you do have to worry about whether the transition lines up with an interband transition or it doesn't line up with an interband transition. Whether you can make these transitions or not will affect the optical properties. And it's actually the detailed band structure that makes copper look copper, gold look gold, and silver look silver. That it has to do with which transitions can be made in between bands in those different materials. Won't go into that in too much more detail. Now, in any of these materials, it's always important to realize that details matter for optical properties. Actually, details matter for many things, so I'll just write that down. Details matter. Sort of a general principle to live by. One detail that matters a lot is the surface. When you look at a material, you see the surface of the material. And very frequently, the surface of the material is not like the rest of the material for one reason or another. A really good example of that is a material like sodium. Sodium is a really good metal. But if you look at its surface, here's a chunk of sodium. The surface of sodium looks kind of gray. It's not reflective. Why is that? Well, because you're not actually looking at sodium. You're looking at sodium oxide. You put the sodium out on the table. Within about an hour, the oxygen in the air has attacked the surface of the sodium. It's formed sodium oxide. Sodium oxide is an insulator, so you're actually seeing a thin layer of insulator on the surface. In this picture, the sodium has been cut in half to open up a metallic surface. And so for about an hour, that surface will look metallic, and then after an hour it will look gray again because you're forming an oxide layer on top of it. So the surfaces matter an awful lot. Frequently the surfaces are not like the rest of the material. Another thing that matters an awful lot is impurities. And we'll discuss impurities a lot in the next lecture as well, or maybe at the end of this lecture if we have time. But for the optical properties, let's imagine we have, okay, here's a empty conduction band, empty conduction band, and then here we have some filled valence band, filled valence band. And that's what our insulator or semiconductor would look like in the absence of impurities. But if I add some foreign impurities into the material, it can actually add eigenstates in the middle of the gap at energies that are somewhere in the middle of the gap. So these are impurity eigenstates. Due to the presence of the impurities. In the absence of those impurities, this material might be transparent if it has a big gap. But when the impurities are there, then you can make some number of transitions of some frequency up to the impurity and back, so that you can get certain colors, modifying the transparency of your material. So even with a weak, very small number of impurities, this can make a huge difference. So here's a classic example: is the material diamond, which everyone's familiar with. Diamonds are gold's best friend, or whatever the phrase is. Wasn't that a James Bond movie or something? Anyway, diamonds are forever. What was the James Bond? Anyway, never mind. So with diamond, a pure diamond is completely clear, whereas if you add just a couple of impurities, this is 1 boron impurity per 10 million carbon atoms, and it turns the diamond somewhat blue. This is a rather famous blue diamond. It's the Hope diamond, estimated value of $250 million. It's sitting in the Smithsonian Museum in Washington. It's also supposed to have a curse associated with it, so don't go try to steal it. It's very bad for you or something. Anyway, if you add a nitrogen atom per 1 million carbons, it turns the diamond a rather yellow color. This is the Tiffany diamond, also highly valuable, owned by the Tiffany company, and I believe it's in their store in New York. Estimated value, well, it's probably a lot more than 12 million now. It's a rather large, beautiful diamond, and it's coming entirely, the color of the diamond is coming entirely from impurities. Now, these diamonds were actually mined. They were dug out of the ground, out of mines. But in fact, in the modern era, we're very good at making materials synthetically in laboratories. You can make a perfectly good diamond with no impurities whatsoever in your laboratory. They're known as synthetic diamonds. They're a lot cheaper than mining them out of the ground. And if you want it to be blue, you just add boron. If you want it to be yellow, you add nitrogen. If you want it to be some other colors, you can make it pink. You can make it whatever color you want by adding the appropriate impurities that put it in the right impurity eigenstates. The advantage of the synthetic diamonds are, well, they're cheaper. They're actually more, they have fewer, you can design the impurities. You can put whatever impurity you want in it. You can keep the impurities out so it can be as pure as you want. And in fact, if you buy synthetic diamonds, you do not support any wars in Africa. So if you're planning on buying diamonds, please, somehow the diamond industry wants you to believe that somehow the synthetic diamonds are inferior to the natural diamonds dug out of a mine. It's totally not true. It's the same carbon. In fact, the carbon that you grow in your lab is probably a lot purer than the stuff you pull out of the mine. So buy synthetic diamonds. I don't own stock in synthetic diamonds, but full disclosure, I don't. Okay, so let's go on and start talking about what happens once you make excitations of electrons in materials. So again, here's energy. We'll draw the top of here's the top of a valence band, filled valence band. Top of valence band, filled. And the bottom of a conduction band. I've drawn this as a direct gap material, but it could be indirect. It's not so crucial. And it's empty, conduction. Anyway, okay, and so there's some gap energy in between the two. And if I put in a photon in order to excite an electron out of the conduction band, out of the valence band to the conduction band, I then get an electron up here in the conduction band, but I get the absence of electron down here in the valence band. And that is an important thing to have a name for, which is known as a hole, also the name of a good rock band. Absence of electron in otherwise filled valence band. So when you put in this energy to excite the electron up to the conduction band, it could be photon, or it could be actually thermal energy too, can excite if the gap is small enough, so then your temperature is high enough, you can thermally excite an electron from the valence band up to the conduction band. Then what you've done is you've actually pair created an electron in a hole. It's entirely analogous to a positron, analogous to positron, where in outer space, in the vacuum of outer space, if you put in a high enough frequency photon, you could pair create an electron-positron pair. You'd have to put in the 2mc² energy, the mass energy of the electron and the positron. You could create them, and at some time later, the electron and the positron could come back together and pair annihilate and emit a photon, or 2 photons, as the case may be. It's the same thing here. You have to put in the gap energy, and you pair create an electron and a hole, and these things run around in the conduction band or the valence band, and at some time later, they can come back together and emit their energy in photons, or in some other way, they can get rid of their energy, and they come back and they reannihilate. So it's entirely analogous to the idea of an electron and positron pair. In fact, when Dirac wrote down his theory of positrons, he was well aware of what was going on in semiconductors, and he was using this as more or less a model of the picture of positrons. So this is one way you can arrange to get holes in the valence band or electrons in the conduction band by adding energy, either light energy or thermal energy, to excite someone up from the valence band into the conduction band. There's another way you could get holes in your valence band and electrons in your conduction band, which is to get the bands to overlap. Let's see if I've drawn this right. So here's my otherwise filled valence band. If the bands overlap by a little bit, here's EF, then these states will be filled in the valence band, but the states on the top of the valence band will unfill and fill the lowest states in the conduction band. And this is exactly what we saw in the case of calcium earlier today, that the lowest band sort of is not quite filled, and the second band is just starting to fill. And so this becomes a little bit metallic because you have some holes in the valence band and some electrons in the conduction band. Now, actually some useful nomenclature, which is the density of holes in a system, density of electrons in conduction band, is usually called N, and it's called N actually not for number, but for negative charge, N for negative, because the electrons have negative charge, whereas the density of holes in valence band equals P. P for positive charge. That's the usual nomenclature. And whether we create our electrons in the conduction band and our holes in our valence band by adding energy like this or by overlapping the bands like that, it appears that N equals P. So maybe we'll write that down. Does N equal P, generally? Because it's every time I created an electron, I created a hole, and in that picture up there, every time I transferred one electron from one band to the other, I created both electron in the conduction band and a hole in the valence band. So it looks like the answer is yes, but it's going to be sort of a qualified yes. Yes, if in pure material, no with impurities. So we have to sort of think about how it is that impurities change the story here. So let's consider the world's most important semiconductor, silicon. Silicon is what all electronics more or less are made out of. So I'm going to draw it as a square lattice, even though it's not a square lattice. It's an FTC lattice with a basis, but this will, just for figurative purposes, we'll draw it as a square lattice here. These are all silicon atoms. Then we're going to imagine taking one silicon atom and replacing it with another atom. Which atom are we going to use? We'll use something right next to silicon on the periodic table. We'll take phosphorus. Now, so we'll take this atom here and make it into a phosphorus atom, phos. I'm going to write out phos so it doesn't get confused with P. It's unfortunate that the symbol for phosphorus is P, and P is also the symbol for the density of holes. Those are unrelated, just sort of random, happens to be inconvenient, but we have to deal with it. So phosphorus equals, it's a silicon atom plus one proton. It's on the left, it's on the right of silicon in the periodic table, plus one electron, and it has some neutrons too, which we're not so concerned about. So I can take this phosphorus and view it as a silicon plus an additional positive charge plus one additional electron. Okay, so it has an additional positive charge here and one electron sitting up there, 1e sitting somewhere else. Now, what happens to that one electron? This one addition, okay, well, maybe I should talk about the proton first. So this proton, it turns out, and we'll justify this in the next lecture, you can more or less ignore the presence of that proton and just think of it as a silicon nucleus. Yes, it has a charge, but that charge is not so important. What's important is this electron here. Where does it go? Well, the valence band is already filled. We started with silicon. It had a filled valence band. Pure silicon has a filled valence band and a gap, and then an empty conduction band. So this one electron must go into conduction band. So here we have added an electron into the conduction band without adding a hole into the valence band. Let me show you a better cartoon of this. So in this picture, the electrons are drawn as little circles around the silicon atoms, and the fact that there are two electrons next to each other is supposed to depict a covalent bond that holds the two silicon atoms together. The fact that everywhere except for where the phosphorus is, all the electrons are tied up in these covalent bonds is another way of saying that we have a filled band. All the electrons are accounted for, and there's a gap to putting the electrons anywhere else. Now, when you put in the phosphorus can make the same four covalent bonds, but then there's one electron left over. And since the entire valence band is filled, the only place that electron can go is up into the conduction band. Okay? So that's what happens. You can do play the same game with a different dopant. Let's back up to dopants on the other side of silicon is aluminum. We could use aluminum, which is silicon minus one proton. And again, we don't have to worry about the proton too much. We can ignore this. We'll justify that later. Ignore. And then it's minus one electron. So with aluminum, we're missing one electron that we need to fill the valence band. So this adds a hole. Adds a hole. And actually, let me draw okay, here they're using boron, not aluminum. Boron is right above aluminum in the periodic table, so it's chemically exactly the same. So it's the same story. Boron is trivalent. It can make 3 covalent bonds, but there's one electron missing in order to fill the entire valence band. So we're missing one electron. Let me just give a couple terms of nomenclature. I'm sorry I'm going over before we end. So phosphorus is known as a N dopant because it adds an N, adds a negative charge, or a donor impurity, because it donates an electron, whereas aluminum or boron is known as P dopant because it adds a hole, or an acceptor impurity because it accepts, or acceptor impurity, accepts an extra electron. And maybe I should define the word dopant before ending. So dopant is a general word which means a foreign chemical introduced into an otherwise pure compound, otherwise pure material, or pure substance, I guess, to change its properties. To change its properties. A rather general word of particular importance these days, considering the Olympics are going on. Okay, so I guess we'll end there, and we'll start again tomorrow. Sorry for going over.